Hi, I'm Jared Heimer, and I'm going to be doing an analysis of the world's largest rope swing. First of all, we're going to use the energy principle to find out the velocity at the bottom of the swing. So first off, delta E equals work. Work will be 0 because there is no energy being forced into the system or let out by the surroundings. So delta K, change in kinetic energy, plus the change in gravitational potential energy will equal 0. So 1/2 mv squared final minus 1/2 mv squared initial would be 0 because velocity equals 0, plus the change in gravity potential energy. So with the manipulation of the formula, we get the final equals the square root of the gravitational constant times the change in height divided by 1/2. So with that, we plug in the values. 39.62 is going to be our delta H, and which is 130 feet, and velocity final is 27.86. So our next step is going to be calculating the tension force at the bottom on the rope for the rope. So we're going to use the F net, which is calculated to be this, which is mass times velocity squared over the radius. The radius is going to be the length of the rope, the velocity is what we calculated earlier, equals the force of gravity plus the force of tension. We're going to solve for the force of tension, which equals mass times velocity squared over the radius minus mass times gravity. By inputting the values that I stated earlier, we're going to get the tension force equaling 2,263.07 newtons. Okay, now we're going to calculate the tension force at 30 degrees. For this, we're going to use the same formula we used for the tension force last time. So it's going to be this F net value, which is also known as centripetal force. That's going to equal the force of gravity plus the tension force. So F of tension will then equal the centripetal force times cosine 30 minus the gravitational force times cosine 30. We're multiplying it by cosine 30 because we want that angle and the force at that angle. So using trigonometry, figured out as cosine. Alright, so by plugging in the value, specifically the value for R is going to be 34.312 meters, which was found earlier in the last step, and the velocity is going to be 25.93 meters per second, and the final tension force is going to be 1,960.22 newtons. Okay, now the final step we're going to do is calculate the stretch and the Ks value and the stretch for at 30 degrees. Alright, so I had researched that a good quality climbing rope and one that is not going to stretch a lot, because you really don't want a lot of stretch here, is going to be a half rope, and that a really good quality half rope is going to be about 8.9 for stretch. So what I did, I multiplied 8.9%, which translates to 0.089 times the initial length, which is 39.62 meters. That gave me a stretch of 3.52 meters. Alright, so now I needed to solve for the Ks, so I could actually do it for 30 degrees. So Ks times S equals the force, and it's actually the tension force. So solve for Ks, it's Ks equals tension force over the S. So the Ks value equals 642.92 newtons per meter. So now we can solve for at 30 degrees. For at 30 degrees, the tension force was 1,960, and divide that by 642.92 newtons per meter. That equaled 3.05 meters. So here's my computational model of the swing. The velocity and tension were greatest at the center point where the magenta arrow is largest, and the stretch is least at the top where the magenta arrow is smallest. My values were off by about 1 meters per second or 0.5 meters, and thank you for watching. If you have any questions, comment.